Hello. Sorry.
You are a presenter now. Yeah.
Yes.
Okay. Can you see my screen?
Yes.
Yes.
Brilliant. Okay. Hello and welcome, everybody. I'm here to talk about the application of the European Ground Motion Service with regard to urban areas and infrastructure. Using a remote sensing technology based on the data collected by radar satellites, EGMS provides millimeter scale measurements of ground movement across most of the European continent. I stress the service does not cover areas outside Europe, although the radar data to make these products is in fact available worldwide. This is the fifth and final webinar in this particular series on EGMS, with this one focusing on applications in urban areas and on infrastructure. So this is what we'll cover in today's webinar. What is the European Ground Motion Service? Some brief detail as to the underlying technology, followed by a description of the three main EGMS products. We'll then get to the main topic of today's webinar, a focus on urban areas and infrastructure. Finally, I'll mention how to learn more about EGMS before we end with a live Q&A session, so please enter your questions as we go. So let's get started. So what is EGMS? A good question. The European Ground Motion Service is the latest offering from the Copernicus Land Monitoring Service. EGMS products are made from the processing of data acquired by the Sentinel-1 radar satellite mission of Europe's Copernicus program. The service provides continental coverage of millimeter scale measurements of ground motion, presented as high-density arrays of points color-coded by their ground velocity in millimeters per year, and each point has an associated time series plot. As with all Copernicus services, EGMS products are openly accessible and entirely free of charge to everyone. So what does EGMS actually measure? EGMS products provide measurements over time of the millimeter scale movement of ground-based features that just happen to reliably reflect the radar signal back to the satellite. These ground-based features may be natural, such as bare rock, or anthropogenic, such as buildings and infrastructure, and they can make up high-density arrays of measurement points, each with an average velocity and associated time series. Such products allow us to measure and map a variety of ground motion phenomena, or rather geological hazards, such as subsidence through, say, mining or clay shrink swell, landslides, uplift from, say, underground gas storage, the stability of larger scale infrastructure, including bridges, dams, roads and rail, power stations, also the surface effects of tunneling and underground construction. EGMS will help build awareness of geological hazards across Europe and support more sustainable choices in planning and development and in the management of land resources, buildings and infrastructure. So briefly, how to access EGMS products. The EGMS Explorer viewing tool, accessible via your browser, allows you to view, analyze and download the EGMS data. In the top right corner of the Explorer, there's a toolbar that provides a number of functions, including point and click time series analysis for every point, averaging of point clusters, changing the legend and viewing parameters, data download and more. Note that data download is performed on a per tile basis and not currently for a user-defined area. This means you'll receive blocks of data that intersect your research area. This issue should be solved in the future. No registration is required to use the Explorer for visualization and analysis. However, the download of data does require registration using the EU login system. Here, you can either create a new account or log in with an existing EU login account. Let's take a quick look at the technology behind EGMS. The data for EGMS products is collected by the Sentinel-1 mission, which comprises of two identical radar satellites in a near polar orbit, 180 degrees apart. They're in this configuration to double the frequency of data collection. Radar satellites are active in as much as they emit pulses of electromagnetic radiation and then record the strength of the return, its time delay, and importantly for our purposes, the phase, that is, the angle of the signal's sine wave as it returns to the satellite. The active nature of the instrument and the wavelength of the radar signal means that data can be collected at night and through cloud cover, so acquisitions are 100% reliable. EGMS products are made from hundreds of repeat image acquisitions over the same locations across the whole of Europe. EGMS products are made by processing stacks of Sentinel-1 radar imagery that are taken over the same place over time. This mission acquires data over Europe typically every 6 days, but 12 at worst. I ask you to imagine our satellite orbiting the Earth, collecting dozens of images of the same place over time. During one orbit, it images a building. The next time the satellite comes over, the building might have subsided, and this is sensed by the satellite as a difference in the phase of the signal returning. It is this interference in the phase between images that gives us the name interferometry. In EGMS, thousands of images acquired since 2015 all over Europe have been processed. In this special interferometric processing, arrays of points are identified that represent features on the ground which we can make these precise phase change measurements. Not only do we know the average velocity of each point, but we also have the time series plot for each one. And this reveals motion trends, accelerations, when movement started or stopped. So what do these data actually look like? Here we can see some EGMS data points superimposed over an optical background. They're color-coded by their velocity, green being stable, cold or blue colors moving towards the satellite, and warm colors, red and yellows, moving away from the satellite. There are two key points. By definition, these ground features, or EGMS measurement points, must have been spectrally stable throughout the period represented by the dataset. Otherwise, the algorithm would reject them. Therefore, EGMS data is much denser over built environments and much more sparse over more rural, vegetated areas, where the signal tends to decorrelate between satellite images. The other thing is that we have no choice as to what ground features act as reliable reflectors. We can only filter out noisy data. So in terms of point coverage, EGMS products are made by a rather serendipitous process. The point I want to draw to your attention with this slide is that EGMS data is acquired in what we call the satellite's line of sight. As radar is a ranging technology, the instrument needs to look to one side to build a two-dimensional picture. The significance is that the orientation of any displacement on the ground is projected onto this line of sight, and so the actual direction of movement is ambiguous without some other form of information. However, in EGMS, we do have a workaround. Our satellites are configured in a near polar orbit, and although they might take 80 minutes or so to complete an orbit, the Earth is spinning beneath, and so it actually takes a week or so to acquire a repeat image of the same place. As this graphic illustrates, half the time the satellite is traveling from north to south, looking west. The other half, it's traveling from south to north, looking east. Data for EGMS is therefore acquired in two discrete, nearly opposing geometries. In EGMS, these two geometries, called ascending and descending, have been further exploited to produce purely vertical and horizontal ground motion layers. This removes the ambiguity of the direction of displacement that we have with a single line of sight. Now, let's just summarize the suite of the three main EGMS products. There are three main products: basic, calibrated, and ortho. Basic products have two layers, as we've just seen, acquired at two different geometries, ascending, descending, to provide near opposing look angles. The data are captured from a 20 by 5 meter ground cell and, land cover allowing, are presented at this full resolution. Basic products are relative to a stable reference measurement point. Calibrated products are the same as the basic products, i.e. full resolution, but are anchored to a GNSS framework, making these measurements in effect absolute. Calibrated data are therefore perhaps more user-friendly, for example, when combined with other geospatial data. And for this reason, the relative basic product is only available as a download. The ortho product also has two layers made from the calibrated product to provide purely vertical and east-west horizontal motions. For the ortho product, the ascending and descending data sets are necessarily mapped onto a common 100-meter grid to accord with other Copernicus products. In all products, the time series plot revealing ground motion trends is available for every single measurement point. I emphasize that all EGMS data can be downloaded for use in your own GIS, but currently this is on a per tile basis. We're looking at a more user-friendly method that might be included in future updates. The ortho product is made up of two layers, one showing just vertical motions, the other just east-west horizontal motions. The ortho product is made from the ascending and descending layers of the calibrated product. In the horizontal domain, only east-west motions are in fact provided. This is due to the orientation of the satellite look angle being mainly from the east or west. The ortho product provides an unambiguous direction of movement and so is useful in areas of steeper topography or landslides or anywhere with ambiguity over the orientation of displacement. Plotted on a 100-meter grid to coincide with other data sets, the ortho product may be easier to understand and interpret than the calibrated product, which, although full resolution, provides measurements in the line of sight of the satellite. Just to provide some further clarity, I'm showing this slide to illustrate how ortho products are made and why they are presented at a reduced spatial resolution compared to the calibrated product. As mentioned, ortho products are made from the trigonometric decomposition of the two differing look angles of the calibrated product, the ascending and descending data sets. Due to the near opposing look angles of these two data sets, the arrays of ground features that are mapped are not the same. So to get a single measurement, either vertical or horizontal, a common grid is used and the average measurement of points which fall into each grid square is computed. Ortho products are therefore not what we'd call full resolution, but based on 100-meter grid. This particular size being chosen to coincide with other Copernicus products. Finally, to illustrate the difference in resolution of calibrated and ortho products, here again is Barcelona in Spain, where we can see deformation in several areas, including the airport and the harbour. The top image shows the full resolution calibrated data, while the bottom image, the 100 by 100 meter vertical only data, is from the ortho product. In conclusion, ortho data may be easier to understand, but calibrated data have a better spatial resolution and therefore might be more useful when looking at more localized features. The initial EGMS baseline datasets were released last year, and with the first update done, cover a nearly 7-year period from 2015 to December 2021. These datasets show the ground motions that have occurred within that time frame and only within that time frame. The plan is to update EGMS annually in every third quarter, covering the preceding year. The second update, taking the service to December 22, will be released in the autumn of this year. Limitations. Although an incredible groundbreaking service, EGMS products do have some limitations, and so we'll look at some of the more important ones here. Coverage. The INSAR technique relies on ground features being spectrally stable over time, and as the ground is covered by all kinds of things, some stable, some moving around or changing, the coverage of measurements is consequently not continuous in space. The amount of spectral stability of an EGMS measurement point is shown by its level of what we call coherence, 0 being no coherence at all and 1 being perfect. In effect, coherence is a measure of the similarity of a point from one radar image to the next, and is a measure of the quality of that point. The lower the coherence of a point, the noisier the data, resulting in a higher standard deviation. It therefore follows that reliable coverage is mostly in the spectrally stable built environment, as opposed to vegetated rural areas. Note that coherence level and standard deviation is given for every single EGMS measurement point. More information is provided in the quality control dossier. Next, XY location. Although EGMS measurement points have a millimetric displacement precision, there is paradoxically a meter scale ambiguity over their exact location in space. A measurement might also be the result of multiple bounces before the signal returns to the satellite. It's therefore not safe to say that this measurement point is on the corner of that house. It's better to trust clusters of measurement points that display similar behavior and that might contain the feature of interest. Spatial resolution. EGMS products are made from Sentinel-1 data that are captured from a ground cell measuring around 20 meters by 5 meters. Only one measurement can be obtained from each ground cell, and so this limits the size of features that can be mapped. As mentioned previously, the basic and calibrated product are offered at their full resolution, while the ortho product is mapped onto a 100-meter grid. Finally, north-south ground motions are not measured by the EGMS system due to the near east and west look direction of the satellite in its corresponding ascending and descending orbits. So now we'll get to the main part of this presentation, looking at the utility of EGMS data in urban areas and infrastructure. I'll just take a slug of tea. We have 8 examples to show that cover a range of applications, including bridges, roads, seaports, urban subsidence, tunnelling, sea defences, airports and dams. So let's get started. This is an example of EGMS application over bridges. This particular study focuses on Blackfriars Bridge, which spans the River Thames in London. This is a pedestrian and railway bridge with a solar panel roof. The local geology is characterised by clay and alluvium, which is known to be sinking at around 3 millimeters per year. It's interesting to note that the original contractors in the 19th century went bust in trying to find solid foundations, as the bedrock here is what's called London clay. London clay is also very prone for its expensive seasonal shrink and swell cycles. Note the road bridge next to it on the west is more stable. Maybe this has better foundations. Looking at the time series plot, we can see a strong seasonal element embedded within the overall subsidence. On closer inspection, this shows movement towards the satellite in the summer, when one might expect the clay swelling to have this effect in the winter. So maybe what we're seeing is in fact a thermal effect from the roof of the bridge. Now we turn to roads. This example is of the main E45 autoroute to southern Italy. The road suffers from many problems, and in this stretch, cutting through a mountainous region, we can see substantial motion to the west of around 16 centimetres over 6 years. Even though most EGMS measurement points are only on the road itself, as the road is on a west-facing hillside, we might assume that the motion is due to landsliding. In the central graphic, the satellite is looking to the west, and so the orange and red points are moving away from the sensor. This motion is corroborated by the ortho product time series plot, top right, which is showing purely westerly movements. Italy is a country that suffers many forms of geological hazard, and so it's noteworthy that this particular landslide is not included in the country's national landslide database, illustrating the power and utility of EGMS data. This next example is of the Jeder Weserport, Germany's largest harbour project, located within a natural bay on the North Sea coast. The structure was built upon 42 million tonnes of dredged sand, the compression of which now seems to be causing the subsidence of around 1.5 centimetres per year. Note, there are no EGMS points within the actual freight terminal area on the eastern end of the port, due to the near constant activity and movement of the cranes. The central graphic also reveals some significant motion encompassing the town of Federwadergroden. This is due to pressure imbalances in subterranean gas storage reservoirs derived from depleted salt caverns. This next example is Amsterdam in the Netherlands. The city is infamously built upon peat that oxidizes over time, compresses, thereby causing subsidence. Older structures with shallow foundations are particularly susceptible, where newer buildings with foundations into the bedrock are more stable. Viewing the data behind a measurement point also tells us the height of the point, so we can determine if the motion is from a building or, for example, at ground level. The time series plot, bottom right, shows some substantial subsidence of one of the many levees that protect the city from flooding. What with the risks associated with sea level rise and subsidence from peat oxidation, the rates of subsidence revealed by EGMS can be used to forecast when a particular structure might be flooded if action is not taken. Next, tunnelling. With the growth of megacities and all that entails, there is more underground construction than ever before. It is well understood that tunnelling causes subsidence, and even with, for example, modern grouting methods, it's still difficult, if not impossible, to control all surface deformation. Ground-based instrumentation is used to monitor such settlement, but the density and distribution of such devices cannot reveal the full story in the way that EGMS-type data can, with its wide area coverage and high density of measurement points. This is central London with a portion of the River Thames mid-left. The large ringed area of subsidence is due to tunnelling for a major new sewerage system. Significantly, we can see the broader effects on property in the area. We can also see a broad line of subsidence that accords with tunnelling for the extension to a metro line. Remembering that these data in the main map show averaged velocity, it can be useful to look at the time series plots to gain a better understanding of when any motion might have in fact started or stopped, and this could be useful for insurance and claims of liability. You may notice two lines of data in the time series plot. This is because we're seeing both ascending and descending data. Plus, at this zoom level, the point and click to bring up the time series covered more than one point. If you zoom right in, you can, of course, select individual points. Next, sea defences. We're moving back into mainland Europe to look at the town of Kristianstad in Sweden. Christiansted is mainly below sea level and suffered from major flooding in 1905 and then again in 2002. There has consequently been a major campaign of levee construction to protect the town from further inundation. This example shows the power of EGMS's wide area view to highlight areas of concern. Here we see one of the levees that also carries a railway suffering subsidence of more than 7 millimeters per year, totaling nearly 4.5 centimeters over 6 years. Not only may this be of concern with regards to future flood risk, but might also be a worry to the railway operator. These kind of data can be a great way to help prioritise resources. Now, moving back to Italy and the city of Rome and its environs. Geologically, the area is characterised by marshy coastal plain and the River Tiber Delta. This results in a complex geological setting with recent deposits alternating between high and low compressibility, all meaning that building foundation design is critical. In this example, we have 3 examples of urban and infrastructure application. First is Rome's airport, Fiumicino. EGMS data reveals significant deformation of the airport infrastructure and the southern part of the runways in particular that are subsiding at a rate of around 1.5 centimeters per year. This is due to their construction on unconsolidated organic soil from the reclaimed marshland. The northern part is stable as it was built on a sand barrier that bordered an original lake. Anyone who's flown in or out of Rome can attest to the bumpiness of these runways on takeoff and landing. The second example in this area is the Fiera di Roma Exhibition Centre, which again is suffering from inadequate foundations that are consequently allowing parts of the structure to subside over 1 centimetre per year. The third example from this region is associated with Rome's infamous Line C metro development that has met many issues, not least those relating to the near constant discovery of subterranean antiquities that are ubiquitous in the region. Many Roman features, including the Colosseum, have been shored up to protect them from the effects of the tunnelling works, which passes directly to the north. EGMS data can be useful to confirm whether such actions are indeed effective. Meanwhile, in the time series plot shown, we can see the average vertical only motion of 3 measurement points. This reveals an overall subsidence, but with a notable acceleration during the summer of 2019, probably related to specific tunnelling activity. These last 2 examples focus on dams. This example shows EGMS calibrated data over a reservoir and dam in eastern Spain. There is deformation visible across the width of the southern shoreline, with a clear localized focus beneath the dam itself, moving in the range of around 10 millimeters per year. Many reservoirs and dams can be seen at once in EGMS data, perhaps offering support to a more systematic approach to the monitoring of such large-scale and widely spread infrastructure. You may notice 2 separate lines of data within the time series plot, and this again is, even though this plot is of the average of many individual points, the data is showing the average from 2 separate satellite tracks, hence the 2 lines of data. This final example is of the Poggio Cancelli Dam in Italy. The time series plots reveal 2 things. First is a discontinuity around October 26, when in fact a swarm of earthquakes hit the area. The second is likely related to the not unusual deformations caused by the reservoir emptying and filling. So just to finish on this theme, we thought it might be useful to consider some points when using EGMS data for application in urban areas or within infrastructure. So first is please appreciate that EGMS measurements are obtained from a ground cell measuring about 20 by 5. So if you're trying to make an accurate analysis of, say, an individual normal house, you might want to forget it. Related to this, please consider that the locational ambiguity of each point. In most cases, it's not clear exactly what part of what feature on the ground is making the, albeit reliable, reflection back to the satellite. Next, don't just consider the average velocity data that you're first presented with in the Explorer window. Remember to examine the time series plots for individual or clusters of points, as these reveal hidden accelerations and decelerations that can be vital to understanding the processes involved. Please remember the wealth of tools available to clarify visualization and aid analysis, both in the time series plot window and in the legend window. Be aware of lone, spurious points that might, after all, just be a garden shed tin roof deforming with the seasons. Have more trust in clusters of points which tend to validate each other. There are many processes that can cause and influence ground motion. For this reason, always be cautious when interpreting the reason for any particular EGMS measurement, unless you have other information. Remember, there are more useful data available for each measurement point when hitting the View Data button in any time series plot window. For example, knowing the relative height of a point can help to identify its location. In the spirit of nothing being perfect, all EGMS data points are subject to some level of noise depending on various characteristics of the reflecting ground feature and the processing. It is therefore useful to consider the RMSE value of an individual point under analysis. Finally, the EGMS Explorer window opens with the ortho product by default with the vertical motion layer open. Generally, it's useful to also examine the corresponding calibrated product, as the higher spatial resolution will probably yield further useful information. So look at the ortho and calibrated products together. So that ends our tour of some urban and infrastructure applications. For those who would like to know more, there is a lot of documentation available from the EGMS site, and this slide just shows a selection of some of the perhaps more useful ones. I'd also like to emphasize the existence of the dedicated EGMS help desk that provides support and will answer any questions. The help desk is also there to record feedback about the service so that improvements can be made, so please don't be shy. The Copernicus Land Monitoring Services team are looking for interesting use cases from your work, either with EGMS or for using any of the other services products. If you have something of interest you can share, then please use the link given to provide further information, and we'd be very pleased to consider the work for promotional purposes. Although this fifth webinar ends the current suite of webinars on EGMS and some of its uses, please stay tuned for further events currently being considered and planned. Thank you very much for your attention from me and all my colleagues who have worked very hard on this cutting-edge project, and I'll now hand you back to Base for the Q&A session.